class, this video is on the mathematical relationships between pressure, volume, temperature, and your amount of particles in a gas. Some prior knowledge that we'll need to remember is how to convert degrees Celsius into Kelvin. Well, recall that your temperature in Celsius can be converted into your temperature in Kelvin. All we have to do for that is add 273 to our temperature in Celsius, and that will give us a value in Kelvin. Some other relationships or other things that we'll need to know is the relationships between these variables: pressure, volume, pressure amount of gas, pressure temperature, and your volume temperature. These were the relationships that we discovered during the lab. So I'm going to quickly review them here. When we had an increase in our pressure, that was because we decreased our volume. This is an indirect relationship, which means that our arrows are going opposite directions. So if we increased our volume, our pressure would decrease, and vice versa. Decrease in our volume caused our pressure to increase. When we increased the amount of particles in our gas, that caused an increase in our pressure, because if we have more particles, then we have more collisions, so we have more pressure. This is a direct relationship. I could have just as easily written the arrows downward, so a decrease in pressure equals a decrease in N. That would be the same thing. It does not matter which direction you draw your arrows. The point is that they're facing the same direction. With our temperature, if we increased our temperature, then we had an increase in our pressure. This is another direct relationship. And with our temperature and our volume, we didn't discover this directly, but if we increase our temperature, then our volume increases. And again, vice versa, if we were to draw the arrows opposite direction, it would mean the same thing. The main goal is that these are direct relationships and that your arrows are going in the same direction. This is your only indirect relationship, and that's between pressure and volume. Now, some new information we haven't talked about. Scientists are really lazy, so they use a lot of abbreviations. One of the abbreviations you'll see with our study of gases is this STP. This stands for standard temperature and pressure. Standard temperature and pressure. They have set particular conditions to be the standard. They call the standard 0 degrees Celsius, and standard pressure is 1 atm, which is also 760 millimeters of mercury, or 101.3 kilopascals, but mainly we have that 1 atm and whatever it's equal to, your different units that you can convert between, and 0 degrees Celsius. Now, how can we use this information to actually calculate these values? A few examples. So first, let me talk about this chart. This chart gives all four of your variables: your pressure, temperature, volume, and your amount of gas. There is an initial condition, so this is the starting amount. Then your system will undergo some type of change. That will produce a final amount. So our starting amount, our ending amount after our change. This last row is called the effect or the impact. It's whatever that change caused. It's whatever our change caused. Did it cause an increase in pressure or a decrease in pressure? Did our temperature go up or did our temperature go down? It's the effect that happened. So first, in this example, a sample of nitrogen gas is at room temperature, which is 25 degrees Celsius, and it exerts a pressure of 720 millimeters of mercury. If this sample is cooled to 0 degrees Celsius, what will be the new pressure? It gives us information to start with. It's saying that our sample of gas is at room temperature, which is 25 degrees Celsius, and we have a pressure of 720 millimeters of mercury. That information is going to go into our temperature and our pressure, and we're going to put it under the initial row because that's the information we're starting with. Now, big thing to remember, and I forgot to say it up here, but big thing to remember, all of your temperatures have to be in Kelvin. Before we can plug them into these equations. You have to have them in units of Kelvin, not degrees Celsius. So here, our starting temperature is 25 degrees Celsius. I need it in Kelvin before I can plug it into this chart. So I'm going to take my 25 degrees Celsius, add 273, I get 298 Kelvin as my starting temperature. That's the number I'm going to put here in my initial box for my temperature, 298 Kelvin. It also says that this sample is exerting a pressure of 720 millimeters of mercury. That is the starting amount of pressure that it gives me, so that's what I'm going to put here, 720 mmHg. Your pressure can be in any unit. It could be in atmospheres, it could be in PSI, it could be in kPAs. It does not matter. As long, if it does matter, then the question will specify. Put your answer in units of whatever. For right now, we're just going to leave them in whatever unit it tells us. All right, so those are my initial amounts. If the sample is cooled to 0 degrees Celsius, this is the change that is occurring. This is how I am changing my system, how I'm altering my system. And I'm cooling it down to 0 degrees Celsius. It wants me to find the new pressure. So again, before I can plug it into my table, I have to convert that 0 degrees Celsius into Kelvin. Well, that gives me 273 Kelvin. That is my final temperature, and I'm going to plug that here into my next row. Now, it wants me to figure out what my new pressure is. So I am trying to find this value right here. I'm going to put a question mark for that pressure because that's what I'm trying to find. It has said nothing about volume. It hasn't said anything about the amount of gas that we're starting with. So I don't care about these values here. Unless it gives you information and that information is changing, then we don't care about those other values. All right, so let's look at this effect. First, let's start with the temperature because that's what I have both values for. Started at 298, I cooled it down, it ended up at 273. So by cooling it down, I decreased my temperature. I'm going to draw a down arrow to represent that my temperature is decreasing. Well, if I decrease my temperature, what effect would that have on my pressure? I need to look up here at my relationships to figure that out. So my temperature is a direct relationship. If I increase temperature, I increase pressure, and the opposite applies. So if I am decreasing my temperature, it means that my pressure will also decrease. The arrows are going in the same direction. That's what a direct relationship means. All right, I know that my pressure will decrease when I decrease my temperature. Now I have to go and actually calculate what my new pressure would be. Here's the confusing part. We're going to start with 720 millimeters of mercury because that's the pressure that I'm given. That's what I'm trying to find the pressure of, my altered pressure. I'm going to set this up like a fact and a factor. And my factor is going to be my units of temperature. Now, I've got two numbers here, the 298 and the 273. I know that my pressure should be smaller than what it's currently starting with. So in order for my 720 to get to a smaller number, does my 298 go on the top or does my 298 go on the bottom? Well, let's try it both ways. If I put my larger 298 on top and I put my 273 on the bottom, so this is my larger one. If I plug that into my calculator, 720 times 298 divided by 273, sorry, you couldn't see that plugged in, equals, I get a value of 785 millimeters of mercury. Or if I was rounding sig figs, 786, because I only need 3 sig figs, whatever, 786. Well, that is a bigger number than my 720. My relationship, I could predict that my pressure should decrease. So this is not my answer, which means that I flipped this from what it should have been. If you have big numbers on top, then these values get larger. Well, I want this value to be smaller. I want my pressure to decrease. So let's try it the opposite direction. Let's start with my 720 millimeters of mercury. I'm going to set up my factor so that my 298, that larger value, is now on the bottom. This is my larger number. And my 273 is going to end up on the top. When I plug this in, 720 times my 273 divided by 298 equals, I get a number of 659.59. If I round that to sig figs, let's go 660. This is smaller than what I started with, which is what it should be doing. It should be decreasing. So because this matches my prediction, that's going to be what my answer is. And I'm going to box in my answer so it's easy to find. When we had the larger number that it gave us on the bottom, then it made my answer smaller. This is that proportional thinking, that reasoning, those ratios that we're going to be working on all year. All those big long ratios, which goes on top, which goes on bottom. Think about larger and smaller. What do we want my answer to be? Smaller? If so, divide by the larger number. If we want it to be bigger, we're going to multiply by the larger number. All right, let's try another example. A 10 milliliter sealed syringe is at a pressure of 0.8 atmosphere. The plunger is then pushed into 7.5 milliliters. Calculate the pressure. Well, my initial volume is 10 milliliters, because that's what I'm starting at. It gives me a pressure of 0.8 atmospheres. I push in my plunger so that my volume changes to be 7.5 milliliters. And I want to know my new pressure. So that's what I'm going to be trying to find. I don't have any information for my temperature. I also don't have any information for my amount of particles. All I care about is pressure and volume. Now, what is my volume doing here? Well, it's going from 10 milliliters down to 7.5, so my volume is decreasing. What would decreasing volume cause my pressure to do? Well, if I look back up at my relationships, decreasing volume, it's an indirect relationship. So decreasing volume would increase my pressure. Okay, I've got my prediction, my answer should be higher than 0.8. Now let's figure out what that answer actually is. So 0.8 ATM, I'm going to start with the pressure. I'm going to set up my factor. Now, I want my number to be smaller. My 10 is either going to go on the top or on the bottom. Well, 10 is bigger than my 7.5. So I found out earlier that if I put my larger number on top, my answer gets larger. But if I put this larger number on the bottom, then my answer will get smaller. Well, I want my pressure to increase. I want it to be bigger than my 0.8. So I'm going to put my 10 on top, and I'm going to put my 7.5 on the bottom. Something to notice about our factors. Normally we've been canceling units diagonally. Well, this is milliliters on top of milliliters. Those still cancel out. I've got one on the top, one on the bottom. They still cancel out, which is why I'm left with units of pressure, which is what my answer should be in. I'm trying to find my final pressure. So this still does work. It's a different type of factor that we're using, but it still cancels our unit. It still gives us the unit we're trying to find. Now, when I plug this in, I've got 0.8 times my, oh, again, you can't see that. Okay, there we go. 0.8 times 10 divided by my 7.5. It should give me a bigger number than 0.8, so let's see. 1.06. That's bigger than 0.8. Awesome. Just to double check, if I had flipped these and did 0.8 times 7.5 divided by 10, I would have only gotten a 0.6, which is a smaller answer. That's not what I wanted. Awesome. Kind of hard to think through. I would like you to go ahead and try to work through examples 1 through 3. My answer key is available to check.